Okay, we're continuing with Chapter 10 in the statistics textbook. In this video, we're going to go through the final section of Chapter 10, which discusses how there are two regression lines. Okay, in fact, two regression lines can be drawn across a scatter diagram. For example, a height-weight scatter diagram is sketched in Figure 8 below. The left-hand panel shows the regression line for weight on height. This picks off the centers of the vertical strips and estimates the average weight for each height. The right-hand panel shows the regression line for height on weight. This picks off the centers of the horizontal strips and estimates the average height for each weight. In both panels, the regression line is solid and the SD line is dashed. The regression of weight on height seems more natural for most purposes, but the other line may come in handy too. All right, so what are they talking about here? What they're saying is when they say there's two regression lines, they're talking about within the exact same chart. And what I mean by that is, so if we have weight on height here, height as on the horizontal axis, if we flip these two, if we put weight on the horizontal, height on the vertical, that's a different chart. As we know, when you do that, that's the inverse. All of the data points are going to flip about y equals x. Okay, so that's not what they're talking about. They're talking about on the exact same chart, there's two regression lines. So how does that work? Well, okay, when we treat height as the independent variable and weight as the dependent variable, then the regression line works just like we've learned. You're picking a height. It's like you bring in a new person and you measure their height, and then you can kind of think about drawing in a small interval around that, a really small interval around that height value, and then there's going to be all these data points that are within that vertical column. And as far as the regression point for weight, you take the average of the y component of all those data points, and that's the point of regression for the weight. That's what you would predict to be the weight of the person. Okay, but now whenever we are the other, and that creates the regression line, right? That's where when you do the whole start at the point of averages and create a line with slope r sigma y, r times sigma y over sigma x, that line is going to be the best estimate for all of those points of averages. Okay, but we could also look at this from the perspective of that's the one regression line. The other regression line is if we look at this from the perspective of weight being the independent variable. So you bring in a new person and they have a certain weight. You go to that weight and now you draw an interval around that weight. Okay, and now to predict the height, you take the average of all the height values within this horizontal column, and that's the regression point for the height. And it's weird to think about, but these are going to be different regression lines. It's weird to think about because, I mean, shouldn't they be the same? I mean, if you take a certain person comes in with a certain height, you predict their weight, but vice versa. If you're going to predict a certain person comes in with that same weight, you should predict that same height, right? So it's kind of a head scratcher. And so here's the regression line for whenever weight's the independent variable. Here's the regression line for whenever height's the independent variable. And you can see the regression line for height as the dependent variable is steeper than the regression line for weight as the dependent variable. We know that the regression line in general is always is less steep than the SD line, but when you do it the opposite way, it's actually always more steep than the SD line, or equal to, or they're the same line. Now, but you might be wondering, well, what about the SD line? If we switch what we label as the independent variable and dependent variable, does that change the SD line? No, it doesn't. So let's go to Excel and break this all down just to see how everything works. Like, why is the SD line not changing? Why does everything turn out the way it does? And we'll even take a look at what happens if you do take the inverse and you flip the weight and height. What does that result in as far as the SD line, etc.? But let's focus on a single chart right now where we're not taking the inverse or anything. It's the same set of data points, same location, and all for everything. So, okay, I pulled these heights and weights from some like data source sample online. So it's like 1,500 heights and weights. All right, here's the averages and standard deviations of the heights and the weights, and then here's the correlation coefficient of the height and weight data, and you can just use the correlation function in Excel. But this is, if you calculated this like we learned how to calculate correlation coefficients in chapter chapter 8, you get the same result. Okay, so the correlation coefficient is 0.5. And what I, after I plotted this data, I just to note, I started off by just inserting a trend line straight from Excel. So you just right click on the data points and go to add trend line, and then add a linear trend line, and then add the equation. So this is the regression line. That's the trend line. But it's for with height as the independent variable. I don't think they have an option to do it with the vertical axis as the independent variable, the regression line. But this is the regression line for height as the independent variable. And so here's the equation for that line. So let's just, we're going to calculate the slope of the regression line and see if it matches up, because maybe they're doing this with like least squares or something. So let's just see what happens. But then this, okay, here in green is the SD line, and then this is the regression line for having weight as the independent variable, which I had to manually put in there. So I'll show you how I did that. Okay. So, but why doesn't the SD line change if depending on what we label as the independent variable and the dependent variable? And it doesn't change, but okay, but then why does the regression line change then? Okay, the reason why the SD line doesn't change is because we know that, okay, here's the point of averages in the middle. So I just plotted that with, just added a separate, you've got the point of averages is just 1 point with the two average values. And there's the data points, and there's the different lines. So yeah, to plot the two lines, the SD line and the XY regression line, I just had to, once I got the point and the slope of each of the lines, I just had to create a second point off the point of averages and then just do a trend line through those 2 points. So, okay, we know that, so any regression line or SD line is going to go through the point of averages. Okay, but now we need to so we have a point, now we just need a slope. Once we have a point and a slope, we have a line. Well, we know the SD line is really simple. It's just the slope of the SD line is sigma y over sigma x. And then, but you have to manually add a negative if need be. This is positive sloping, so we don't add a negative. There's the SD line, slope. And so with that, I've got a point and a slope, plotted the SD line from the perspective of x as the independent variable. So what happens if we treat the y-axis as the independent variable? Well, all we're doing is, when it comes to the SD line, we're saying that you start at the point of averages. If you go 1.5 standard deviations in the x, then you need to go to get to the SD line, you need to go 1.5 standard deviations in the y. That's the whole point of the SD line. It's the same. You're the same number of standard deviations in both the x and the y away from the average. So when we treat the vertical axis as the independent variable, the slope is sigma x over sigma y, and all that means is that if you go a certain amount in the y direction, certain number of standard deviations, and then to get back to the line, you go that same number of standard deviations in the x. So it's the same line. Now you might be kind of scratching your head thinking, but wouldn't it work out the same way with the regression lines? No, it doesn't. So let's take a look at the regression, how the regression lines work. So we know when it comes to the regression line, the regression lines go through the point of averages, but the slope, it takes into account the correlation, the degree of scattering around the SD line. Okay, so the way this works is that if we think about just the normal regression curve with x as the independent variable, so we go a certain number of standard deviations in the x. Okay, let's go in the negative direction. Why not? Certain number of standard deviations in the x. and this is in the negative. So this is a negative amount. All right. Now, instead of going that same number of standard deviations in the negative y, we have to do negative, negative, because it's a positive slope to get back to the line. We say we're going to go 0.5, the correlation coefficient times that number of standard deviations in the y in this case. And now we're on the regression line, right? We're always, in this case, we're always halfway between the regression line is always, since the correlation coefficient is 0.5, the regression line is always halfway between the horizontal and the SD line. Okay? So now, if we look at this from the perspective that 0.5, what that 0.5 is doing is taking into account that we're trying to get the averages here, right? We're not, we draw this vertical column at our X point that we chose or brought in. And then so now if we went to the SD line, we would be the point of averages of all those Y values in that column, this would be too low. That's what the correlation coefficient is helping us with. That point of averages of the, not this point of averages of that vertical column. Okay, so if we keep that, the whole purpose of the correlation coefficient in mind, then if we, the slope of the regular regression line is R times sigma Y over sigma X. Now the slope of the regression line with respect to the vertical axis being the independent variable is going to be R sigma X over sigma Y. And you might think, well, no, wouldn't it be sigma Y over R, or no, sigma X over R sigma Y, which would result in the same regression line because we're looking at, it's kind of like we're turning our head on our sides and treating this like it's kind of like it's the horizontal axis, right? But no, that's the difference. If it was sigma X over R sigma Y, it would be the same, the line, the two regression lines would match up, but that doesn't make sense as far as the purpose of the correlation coefficient in this respect. So if we this is the independent variable and we turn our heads on our side, okay, you've got you go a certain amount in the Y, right? That's like that's the input, because we know the Y, that we're inputting the Y. So we go a certain number of standard deviations in the Y. Now, how do we apply the R? We don't multiply the R times sigma Y. We're multiplying the R times sigma X, right? Because we would typically go that same number of standard deviations in the X, that would get us to the SD line, but the purpose of the R is to account for that scatter. So we multiply the R times sigma X, and now we're on the regression line, and that's why they're different. These two slopes here for the SD line are just reciprocals. So, like, you know, you look at this and say, well, these are different slopes. Same point, different slopes. They should be different lines. No, because we're looking at it's like we're turning our heads and treating this as the independent variable. So the fact that these two are reciprocals, it makes it the same line. And that's exactly what would be the case here if these two were reciprocals, but they're not reciprocals. This is not sigma X over R sigma Y. This is R sigma X over sigma Y. That's the difference. We didn't flip the R. Okay, so that's where it comes from. Now, okay, if we look at the equation that Excel gave for the regression line, well, we can see there's the slope of the regression line with the height as the independent variable. They match up. The slopes match up. Exactly. Now, you might wonder, well, wouldn't Excel use like least squares? Well, okay, we haven't gotten to least squares yet, but that's a good question to ask. We'll talk about that when we get to least squares, right? But we can see here, just using the standard regression method, R sigma Y over sigma X as the slope and the point of averages as the point, right? Point slope. We get the equation that Excel calculated. Now, if we add in this equation here, okay, is this the equation of the line? No, it's not, because we need to take this and solve for X. That's the only difference. This needs to be, I mean, this is the equation. This is obviously the equation of the line, but the whole idea is where the Y is the independent variable. So yeah, this is okay. Yeah, this is not wrong, but we would want to solve for X. Okay, we can take a look at the equation of the SD line. And yeah, there's that 5.9312. And if we solve for x, we would get this slope. Okay, now, what happens if we do take the inverse of this? So we put weight on the horizontal and height on the vertical. That is a different graph. But how are the resulting regression lines related? Well, okay. Here's the inverse. And here's Excel's regression line. And I didn't put in the point of averages, but somewhere in there. Okay, but the point of averages is going to be different in this case. It's going to be the same numerically, just the numbers flip, but it's different, right? Instead of 68, 127.4, it's going to be 127.468. All this data is flipped about y is equal to x. You take this and you flip it about y equals x. That's how inverses work. Okay, so what is this 0.084 slope going through the point of averages? Well, okay, we know that this regression line here is for height on weight, right? And we know that this orange regression line is for height on weight. But in this case, we're kind of looking at it, we have to turn our heads, right? So this slope is 11.903. So if we did solve for x, what would the slope be? If we took this and solved for x, what would the slope be? So all we need to do is take 1 divided by 11.903, 0.084012. There you go. So interesting, but that is now, okay, are those the same line? Is that the same regression line? Because again, what that's saying is that what this means is that if you turn your head and think about so it's going to be positive. If you turn your head and now this is going in the positive direction, this is sloping up at 0.084. So is this line and this line the same line? Well, first of all, they're going through a different point of averages, right? And second of all, this is 0.084 with respect to the independent variable being on the x. And this is 0.084 this is 11.903 with respect to the independent variable being on the x. So all it is, it's flipped about y equals x is what it is, right? This bottom portion flips up over here over y equals x. This flips down. You see? So everything flips. All of the SD line is going to flip about y equals x. The regression lines are going to flip about y equals x. Everything flips. But we can see the slopes and whatnot are still kind of related. And that this is, you just take they have the same. And that, so they have it's weird to think about. They have the same slope, but just one is when you're looking at the vertical as the independent variable. The other is when you're looking at the horizontal as the independent variable. Now, but just to think about, but now just one thing to note though, the slope of the SD line is not going to flip because the slope of the SD line is independent of which axis you're choosing as the independent variable. So the only thing, when it comes to the SD line, the only thing that flips is the point that it goes through. The SD line is going to have that same slope, but just instead of going through the point of averages over here, it's going to go through the point of averages over here. Okay, let's take a look at this example. IQ scores are scaled to have an average of about 100 and a standard deviation of about 15, both for men and for women. The correlation between the IQs of husbands and wives is about 0.5. A large study of families found that the men whose IQ was 140 had wives whose IQ averaged 120. Look at the wives in the study whose IQ was 120. Should the average IQ of their husbands be greater than 120? Answer yes or no, explain briefly. Okay, so what they're asking is, we've got this data for IQ scores of men and women on the vertical, men on the horizontal. For a men's score of 140, the wives averaged around 120 IQ score. That's like based on the regression line, right? So they're just saying, okay, well, when for the case where you have a wife whose IQ is 120, what did the men average? So what, like for the opposite regression line, if you're treating the wife's IQ as the independent variable, what did the men average? So okay, if we bring in the chart from the Excel sheet, just to try and get a sense for this, this is obviously different data, but okay, if we're 140 was a little bit above average, so that's the incoming variable, so somewhere around here. Okay, and then there's the wife's average. That was like they're saying is 120. So this was like 140, then the average was 120. So now they're saying, okay, well, if the independent variable is 120, what would the average be for the horizontal? So we use the other regression lines. That would be here. So it's going to definitely be like in all cases for a football-shaped cloud, in all cases, the regression line with respect to the with vertical and horizontal is going to be more or less steep than the regression line with respect to horizontal and vertical. So we know for sure this for the wife's weight of one or IQ score of 120, the men's IQ score is going to be less than 140. But they're not asking if it's going to be less than 140. They're asking if it's going to be less than or greater than 120. Okay, so let's see. Well, okay, we would need the line y equals x would be helpful because that's where we can see where husband's IQ is equal to wife's IQ. I mean, this isn't even the chart. But, okay, we have to take a look at the actual chart. But we do know for sure, just from this chart, that the incoming husband's IQ for the first analysis was 140. Wife's IQ and average was 120. But now looking at our incoming wife's IQ of 120, we know the husband's IQ is going to be less than 140 for sure. But is it less than 120? We need to look at the chart. So let's see. Is it going to be greater than 120? The answer is no. The average IQ of their husbands will be around 110. See the figure below. The families where the husband had an IQ of 140 are shown in the vertical strip. Okay, there's the 140 IQ. Okay, the average Y coordinate is 120. Yep. The families where the wife has an IQ of 120 are shown in the horizontal strip. Okay, this is a completely different set of families. The average X coordinate for points in the horizontal strip is about 110. Remember, there are two regression lines. One line is for predicting the wife's IQ from her husband's IQ. The other for predicting the husband's IQ from the wife's. Yeah. So it is a little weird to think about. I mean, shouldn't they line up, right? The best prediction for a husband's IQ of 140 is a wife's IQ of 120, but vice versa. The best prediction for a wife's IQ of 120 is a husband's IQ of 140. But we're seeing here doesn't quite work out that way. So we'll have to talk about this more as we continue through this section, this chapter and the upcoming chapters. Okay, but we would to get this answer, we would need the chart. Because, again, we know that the average husband's IQ for a wife IQ of 120 is going to be less than 140, but we needed to see if it was, in fact, well, okay, we might have been able to figure this out. Did they give us the average? The average IQ of both was 110, because we could guess that that if we're above average, we're going to then going between regression lines, we're going to stay above average, right? If we were above average for a husband's IQ and predicting the wife's IQ, which is going to be above average, right? The regression line goes through the points of averages. So if you're above average with respect to the X, you're going to be above average with respect to the Y. But then when you go the other direction, yeah, it's going to change, but you're still going to be above average. But that wouldn't have helped us here because the average was 110. The question was, would we be greater than, let's see, 120? So you have to take a look at the chart to see the exact answer. But okay, let's take a look at the exercises. For the men age 18 to 24 in the Haynes 5 sample, the ones who were 63 inches tall averaged 138 pounds in weight. True or false, and explain. The ones who weighed 138 pounds must have averaged 63 inches in height. Okay, now this we can answer, right? So you see what it's saying here. Let me bring this chart down. So it's asking for this study, the ones we can answer this and we don't need the chart, because it's saying the ones who were 63 inches tall average 138 pounds in weight. That's the x-axis mapping to the y-axis. True or false, and explain. True or false, the ones who weighed 138 pounds also averaged 63 inches in height. So we're assuming this is a football-shaped cloud. Well, no, it doesn't. It doesn't. It's not a one-to-one mapping back and forth. So, okay, are we above average here? Well, it doesn't even matter. We just know it's not going to, no matter if we're below average or above average, if this 63 inches is below or above, it's not going to be a one-to-one mapping unless we're on the point of averages, which I'm assuming we're not. What is 63 inches? 5'3"? No, we're below average. So this is going to be false. It's not a one-to-one mapping between the x and the y variables. Now, if they asked us, something slightly different, right? The input was this, averaging to this. Now, if we stayed at that, if we took that average as the input, would the mapping to the output as the horizontal axis, it would be something a little bit different than what we started with? Then we need the actual chart. Okay. In Pearson's study, the sons of the 72-inch fathers only averaged 71 inches in height. True or false? If you take the 71-inch sons, their fathers will average about 72 inches in height. Explain briefly. Okay, no. Same exact the concept as what we just talked about. It's asking about a one-to-one mapping here. The sons of the 72-inch fathers were coming in at 72 inches. Okay, and then we find what that average is. That's what the regression line is all about. So now they're saying, okay, if we stayed with that 71-inch sons, that's the y-axis, and took that as the independent variable, would the fathers average that same height that we just looked at with respect to the x-axis, the independent variable? No. And so this is above average. It's going to be this. We know the sons are going to, the fathers are going to be less than 72 inches in that case, the average. So false. Okay, in example 2, in a previous section, the regression method predicted that a student at the 90th percentile on the SAT would only be at the 69th percentile on first-year GPA. True or false? A student at the 69th percentile on the first-year GPA should be at the 90th percentile on the SAT. Okay, well, we know that where this percentile phenomena comes from in relation to football-shaped clouds is the fact that, so if we were if the regression curve was on the SD line, then the percentiles would match up. You can look at the percentile from the perspective of the number of standard deviations you are away from the average. But because if we come in at a high percentile, that's like what are we talking about here? The SAT score is at a high percentile. Well, okay, but where are we at with respect to the y-axis as far as percentile? We're a certain number of standard deviations away from the average in the x, but we're a lower amount of standard deviations away from the average in the y, right? Because it's like the correlation coefficient times the sigma y. So that's why it's if you have a 90th percentile in the SAT, that's the x-axis, then on average, you're going to be in a lower percentile with respect to the y-axis variable. Okay, so now what they're saying is if we're treating the x or the y-axis as the independent variable, so we're in the 69th percentile first year GPA, so we're above average, above the point of averages, so we're like somewhere over here, right? Then should we be at the 90th percentile in the SAT? No, look, we're below the SD line. We're going to be at a lower percentile with respect to the in this case would be the dependent variable axis. So false.